Hello everyone, this is lecture 7, least squares criterions. In the last lecture, lecture 6, you look at two different criterion, which is Cheryshev criterion and the sum of the absolute deviations, right? So those two criteria help you determine the value of the parameter of the functions to fit into the data set or the collection of data points that you have. In this lecture, we focus on another criterion, the least square criterion. This is probably the most widely used criterion in all the mathematics and statistics that helps determine the parameters of the function to fit the curve of the function into the data set. Okay, and because of the importance of the criterions, I'm going to actually derive the formula for the parameters, and we're going to do some calculations to find the equations of the function or the value of the parameters, so that we can derive or obtain the explicit representations of the functions. Okay. And because the derivations of the least square criterion or the parameters of the least square criterion require a lot of previous knowledge, and one of that is the distance between 2 points and the partial derivatives. Right? The distance between 2 points can be easily obtained, and a lot of you may have seen that before. However, partial derivatives probably a new topic to a lot of you. So the partial derivative is just the derivative, but for function of more than one variable. So I'm going to write down the formula for the distance between 2 points and partial derivatives, and I'm going to do a couple of examples related to partial derivatives before we jump into the least square criterion and derive the formula for the parameters of the functions for the least square criterion. All right, so the distance between 2 points, all right, so the formula of the distance between 2 points, x1, y1, and x2, y2 is d, right, we call that the distance, which is the square root of x2 minus x1 square plus y2 minus y1 square. If you take the square of both sides of this equation, you get that d square equal to x2 minus x1 square plus y2 minus y1 square. So this distance can be derived from the Pythagorean's theorem. So we just leave it like that. This is the formula that we're going to use later on. I want to mention that eventually you can also use this for the sum of the absolute deviations or the absolute deviations in general. The next formula we're going to look at is the partial derivatives. Right? Again, partial derivative is just the derivative or differentiations of the functions for more than a function of more than one variable. So in this case, we're just going to focus on the function of two variables. Right? So this is the function of x and y. So in this case, x and y are both independent variable. So let me quickly say that. So independent variables. Another way to say independent variables are input, right? So that's the input that you're going to put in, you do the calculations, and then you obtain an output or the dependent variable. So z is the dependent variable. All right, so you can apply the derivative of or the partial derivative on this function of two variables. And the notations that we're going to use for the partial derivatives is as follows. So this is the curly d, right? So another way to say is the fancy d. So you say pronounce partial, so partial z, partial x. This means this is the partial derivative of z of the function with respect to x. We do partial derivative because you have two different independent variables. So this is the partial derivative of z with respect to x, and this is the partial derivative of z with respect to y. So for partial derivative of z with respect to x, and now the notations that we use is partial f, partial x, or f sub x. Okay, either one should be fine. Right? It depends on the person who wants to use it, or it depends on the textbook that you read. It doesn't matter to us which notation that we can use. So for the partial derivative of z with respect to y, we can also say partial f, partial y, or f sub y, like this. Okay. Another way to do it is just say partial x of the function f of x comma y. Here you do partial y of f of x comma y. Right, it's the notations. So how would you find partial derivative of the function of more than one variable? So in this particular case, we just consider a function of two variables, right? To find the derivative or find the partial derivative. So to find, let's see, f sub x, oh, this is partial derivative of f with respect to x. We regard y as a constant, right? And differentiate f of x comma y with respect to x. Right, so that means that in the function of two variables, now if you want to take partial derivative of the function with respect to x, you consider y as a constant. So y can be -10, y can be 3000, right? It's just some constant, right? Just keep in mind that y in this context is a constant and only x is the variable when you want to find the partial derivative of f with respect to x. And then similarly, when you want to find y sub f sub y, we regard x as a constant, and you differentiate f of x comma y with respect to y. And that is how you obtain the partial derivative of the function with respect to x or with respect to y. Now, we're going to do some example related to partial derivatives, right? And this is where I assume a knowledge of calculus because you need to know how to take the derivative of the function with respect to a variable. Okay. So partial derivative of f with respect to x, right? So let me begin again here. So if the function given to you has the form x cubed plus x squared times y cubed minus 2 times y squared, then you ask you to find partial derivative of f with respect to x and partial derivative of f with respect to y. So what we can write is f sub x, or another notation is partial f partial x. And the function f is x cubed plus x squared times y cubed minus 2 times y squared, right? So you take partial derivative of the function with respect to x. That means you consider y as a constant, right? So in this case, y cubed is a constant. This term is a constant. Let me quickly note that. So this is this term constant. Okay, and then you just take derivative with respect to x. So derivative of a sum is sum of derivative, and derivative of a difference is difference of derivative. So that's give me, so derivative of x cubed is 3x squared, And derivative of this term, remember y cubed in this case is a constant. So you just take derivative of x squared. So this give me 2x times y cubed. And the derivative of a constant, right, is equal to 0. So that's what we get for derivative of the function with respect to x. Now we move on to the second part, which is partial derivative of the function with respect to y. Well, you do partial f, partial y equal to partial y of x cubed plus x squared times y cubed minus 2y squared. Again, in this context, you regard x as a constant and you differentiate the function with respect to y. So here, this is constant. This is constant. Now you take partial derivative of the function with respect to y. So partial derivative of x cubed is going to be equal to 0. Partial derivative of this term is going to be plus x squared times y. So y cubed is going to be 3y squared. And the derivative of this term is -2. Right, so y squared becomes 2y. Right, so if you simplify this a little bit, you get 3 times x squared y squared minus 4y. Right, so that's the partial derivative of the function with respect to a certain variable. And it's the most that we're going to do with the partial derivative. We're not going to complicate our problem. The idea for this exercise is to help us understand the partial derivative a little bit so that we can use that to derive the formula for the parameters used in the model that we want to fit into the data points. All right, so let's do another example. Gonna find, again, give it a function of 2 variables. We find the partial derivatives and then evaluate the partial derivative at a point. All right, so here you have a function of the form 4 minus x squared minus y squared. And we want to find the partial derivative with respect to x and with respect to y. And then later, we're going to evaluate this partial derivatives at the point 1, 1. All right, so y sub x is equal to partial f, partial x, or partial x of 4 minus x squared minus y squared. All right. So remember, take partial derivative of the function with respect to x. You consider y as a constant. So this term is a constant. So now you say that, okay, take partial derivative of this function. Partial derivative of the sum is the sum of partial derivatives. And partial derivative of a difference is difference of derivative. So partial derivative of 4 is equal to 0, right? Because derivative of a constant is 0. Partial derivative of negative x is going to be negative or minus 2x. And partial derivative of y of a constant here is also equal to 0, so minus 0. So you have negative 2x as the answer for partial derivative of f with respect to x. Now you find the partial derivative of f with respect to y. So partial f, partial y, or partial y of 4 minus x squared minus y squared. So again, right, so in this context, x is a constant, right? So this is the constant. Now you take derivative, you get partial derivative of 4 with respect to y is 0. Derivative of this constant is also equal to 0. And the derivative of negative y squared is minus 2y. Or this is minus 2y. And then you can evaluate this this partial derivatives at a point, right? So the given point in this case, 1, 1. So I do f of x, f sub x of 1, 1 is -2 times 1 equal to -2. And f sub y 1, 1 is -2 times 1 as well. It's -2. All right, so this is a whole, I know it's not as the extensive problems that we need, but at least give you some idea of how partial derivative operated, right? All right. Eventually, we're going to use the knowledge of partial derivative to derive the formula for the parameters of the function. All right, so let's talk about least square criterion. Right, so this, again, probably the most frequently used curve fitting criterion in all the mathematics and statistics. So the problem is to determine the parameters of the function y equal to f of x to minimize the sum right. So the summations of the absolute value of y sub I minus f of x sub I, right? And you square this, right? You find the distance between the point you observe and the point that you get from the line. You square it and take the sum, right? This is for I going from 1 to n, and I call this summation S for n data points, x sub I, y sub I, where I is going from 1 up to n. Okay, so this is the conditions or the criterion that we're going to use to derive the parameters, to help us derive the parameter. Okay, so let's derive a formula for the parameters of the functions that we want to use to fit into n data point. The first functions that we're going to consider is just a straight line, right, or linear functions of the form ax plus b. So that is, suppose a model of the form y equal to ax plus b is suspected, and it has been decided to use the n data point to estimate a and b. Now we're going to apply the least squares criterion to the line, and it's going to provide it with this following information. So S right here, this formula is equal to the summations for I going from 1 to n, absolute value of yi minus f of x sub I square, or in this case, the distance square. And f of x sub I is equal to ax sub I plus b. Right, so this is the summation for I going from 1 to n of the distance between yi minus a sub I plus b square. Or if you distribute the negative into the parentheses, you get this is the formula. So the summation for I going from 1 to n of distance between a y sub I minus a sub I minus b square. All right, so we want to minimize this particular sum. Right, so the necessary condition for the optimality is that the partial derivatives, right? So why partial derivatives in this case? Because the parameters that you want to look for are a and b. So that is regarded as the function of two different variables or parameters in this case, right? So that's why when you take the derivative, you have to consider partial derivative. And why taking the derivative of this particular conditions? Because we want to find the optimal, we want to minimize this summations, right? And in calculus one, when you learned about optimizations, when you learned about finding the maximum value or minimum value, what you do is you take the derivative of the functions and set that equal to 0, and you solve for the particular value of x. Similar to that, we're going to apply that knowledge into this particular problem, that you want to minimize or you want to find the minimum point of this particular criterion of this summation for that matter. You want to take the partial derivative and set that equal to 0, right? So the necessary condition for optimality is that the partial derivative, so there are two partial derivatives, partial s, partial a, and partial s, partial b equals 0. All right, and it's going to use the following equations. So partial s, partial a. So now we no longer use the absolute value notation because you have a square already. So that's always going to be positive. So what you do is you're going to just use the regular parentheses. Okay, now you take the partial derivative of this. Right? So the partial derivative of the sum is the sum of partial derivatives. So that means when you do the derivative, you can't just ignore this summation for now and just take the individual derivative. So partial s, partial a, meaning that you take partial a of this function. So I set the summation for I going from 1 to n of y sub I minus a times x sub I minus b, and then you going to square this. All right, so again, the partial derivative of the sum is the sum of the partial derivative. So we can take the derivative of this part of the function only. So this is the square. So you're going to bring down the square. So it's become 2 times the summation for I going from 1 to n of a sub I minus, y sub I minus a times x sub I minus b. And then you use chain rule of derivative, and you take the derivative of the function with respect to a for the term inside the parentheses. This is a constant. This is a constant. So the derivative of that is just going, the derivative of this term is going to be negative x sub I. All right. And then you're going to set this equal to 0. All right. Then what we need to do is to get rid of the 2 because it's just a constant. You divide both sides for 2. This is a negative sign. You divide it or multiply both sides for negative sign, and you obtain the following equation. So the summation for I going from 1 to n of y sub I minus a times x sub I minus b times x sub I equal to 0. So that's one equation. We need another equation so that we can solve for the value of a and the value of b. So that's one equation. Here's another equation. Another equation is coming from the partial derivative of s with respect to b. Now this is partial b of summation for I going from 1 to n of y sub I minus a x sub I minus b squared. And this is what very similar to this derivations. Right? So you're gonna take down the 2 summation for I going from 1 to n of y sub I minus a times x sub I minus b. Right. Now you multiply with the derivative of the inside function of this function. Remember, this is a constant. This part is a constant because you take partial derivative with respect to b. So partial derivative with respect to b is -1. You set this equal to 0 as well. And then what you do is you divide both sides for 2 and divide both sides for -1. So you're going to have the second equation here, the summation for I going from 1 to n of y sub I minus a times x sub I minus b equal to 0. So this is the second equation. All right, so you take the first equation, the second equation, you get from the first equation, you distribute x sub I into the parentheses. Right, so you're going to get x sub I times y sub I, then -a times x sub I squared, and then minus b times x sub I. And then you take the sum. Right? So from the first equation, you get x sub I times y sub I minus a times x sub I squared minus b times x sub I equal to 0. And from the second equation, right, there's nothing for us to distribute, so I'm going to keep it the same thing. Summation for I going from 1 to n of y sub I minus a times x sub I minus b equal to 0. Now you break the summations, right? So the sum is going to be, so the first equation becomes the summation for I going from 1 to n of x sub I, y sub I, minus the summations for I going from 1 to n of x sub I, and a does not depend on I, so you can bring that out of the summation, minus the summation for I going from 1 to n of x sub I. And again, b in this case does not depend on I. So you bring that out of the summation. And that's from the first equations. And from the second equation, it's going to be the same thing, right? You break the summation and you get the summation for I going from 1 to n of y sub I minus a times the summations of I going from 1 to n of x sub I minus the summations of b for I going from 1 to n equal to 0. So b does not depend on I. So therefore, you can bring that out of the summations operations. And because of that, this summation becomes b times n, for n is the sum of for I going from 1 to n. So this is what you get. Now you're going to rearrange the terms, right, so that you can have the following equations. So this is one system. Another system we have here. We're going to arrange things around. So we're going to move this to the right hand side and multiply -1 across. You get the first equations become a times I going from 1 to n of x sub I square plus b times the summations for I going from 1 to n of x sub I equal to the summations for I going from 1 to n of x sub I, y sub I. Now you rearrange the second equations by moving this term to the right hand side as well. You get And then multiply -1 across. You have a times the summation for I going from 1 to n x sub I minus b times n equal to the summation for I going from 1 to n of y sub I. And then from these two equations, you can actually solve for the explicit formula for A and B. And that's as much I want to show for the derivation. I'm not gonna spend time going through the detail of how to solve this system of linear equations. But absolutely that you can solve the solution from this solutions of A and B from the system of equations. Here's the formula for A and B. So A is equal to n times the summations of x sub I, y sub I. Right? So I'm not going to write down I going from 1 to n. It's just the, to cut it short, the assumption is that you have n points, right? And the summation is going from 1 to n. This is minus the summation x sub I times the summations of y sub I divided by n times the summation of x sub I square minus the summation of x sub I altogether square, right? And a in this case, the slope. And the formula for b is that of the summation of x sub I square times the summation of y sub I minus the summations of x sub I, y sub I, times the summations of x sub I, and divided by the denominator n times x sub I square minus the summation of x sub I altogether square. And this is the intercept. And we're going to use these two formulas to help with our calculations of A and B to fit the model into, to fit the curve into the data points. Okay. Okay, so here is the example, right? So this is our focus right here, right? So this is the value of A, this is the value of B, and this is the formula works for the linear equation of the form y equal to ax plus b, for A is the slope and B is their intercept. Here you have this many points, so 1, 2, 3, 4, 5, 6 points, and you want to fit the model of the form y equal to x cx to the data set using the least square criterion. Right. And from the least square criterion, you derive the formula for A and B. So in this case, you don't have the intercept, you just have the slope x. So in this case, the x value, the c value is going to be equal to A. So let me set up from the given model. We obtain that c is equal to the same as the A value, or the value of A, and c is going to be n times the summation of x sub I, y sub I, minus the summation of x sub I times the summation of y sub I, divided by n times the summations of x sub I square minus the summation of x sub I altogether square. Okay, because we only have the slope in the proposed model, just c times x, there's no y-intercept, so we don't care about the value of b. So to obtain the value of c, we need to do all of this calculation. We need to do the calculation of x sub I, the sum of x sub I, y sub I, the sum of x, the sum of y, and the sum of x sub I square. So I have this table of value here, and I'm going to fill in the information. And the information can be done either you can use the calculator, do it by hand, or I can use the Excel spreadsheet to help me with the calculations. So the x value is 1, 2.3, 3.7, 4.2, 6.1, and 7.0, or just 7 for that matter. The y value is 3.6, 3, 3.2, 5.1, 5.3, 6.8. So what I'm going to do, I'm going to use Excel spreadsheet to help me with the calculations. Okay, so the next column that I need to calculate, given that the first column is the value of x, the second column is the values of y. The third column is the product between x and y. So what I do is I set equal x times y. And I'm going to track this calculation down toward the end. So this is the values of x times y. Another column that I need to create is x squared. That means you set this equal to 1, right? So this column times this column again. And we track the formula down. All right, so I'm gonna write down the informations in my notes. So x times y, so this is 3.6, 6.9, 11.84, 21.42, 32.33, and 47.6. For x, where I get 1, 5.29, 13.69, 17.64, 37.21, and 49. Okay. Now, part of the formula, I need to find the summation of x times y, the summation of x, the summations of y, the summation of x squared. So for this column, I'm going to hit equal summations, open parentheses, choose on the value in that column x, close the parenthesis, hit enter, and it's going to give you the summation for x. So the summations for x is 24.3. Now you're going to do the same thing for the value of y, but you can just track the formula to the right, and it's going to give you the summations of y, the summation of x times y, and the summation of x squared. So this gives me 27, 123.69, and 123.83. And now you're going to put all of this information into our formula. Remember, you have 6 points in this particular problem, so n is equal to 6. The summation of x times y is from this column 123.69 minus the summation of x is 24.3 times 27 divided by n, which is 6 times the summations of x squared, which is 123.83 minus the summation of x, 24.3 squared. Now, if you do a quick calculation using Excel, so I'm going to set this up, right? So this is equal to, open parenthesis to enter the information on the numerator. So 6 times the summations of x times y, right? Minus the summations of x times the summations of y, close parentheses. We're done with the numerator. Now for the denominator, divided by open parentheses, 6, right? That is the number of points you have, times the summation of x squared, minus open parenthesis. Now you enter the informations of this part of the summation of x squared, right? So open parenthesis, 24.3, then you square it, you close the parenthesis for the square, and then you close the parenthesis for the denominator. You hit enter, and it's going to give you the evaluations of C. So in this case, C is equal to 0.564. So C is equal to 0.564. All right. So the function is of the form y equal to 0.564x. So that means given this data set or the collection of data points, I'm gonna fit the line of the form 0.564x through these points. Right. So this is the calculation by hand, right? You can double check your work by looking at the graph of this of the data point. Right, so collect this 2 columns, hit insert, go to a scatter plot, hit this scatter plot, then click on any point here, right click, and then select add trend line, and it's gonna give you the value of leading function here. And you can display the equations, right? So the idea for this is that you have the slope to be 0.564, right? It's very similar to our calculations. It's just that this is just an estimations, right? It's just the calculation so that we want to practice the calculations of the slope. Eventually, you can do the calculation for the intercept as well. Right, so that's it for us. For this particular problem, we just want to calculate the slope and see what happened. All right. Now moving on. So in the next part of the lecture, we're gonna do the same derivations, but for a power curve or the power polynomial functions of degree m. Right. So this power curve. We're going to apply the least square criterion as well, divide the formula for the parameter. In this case is the parameter a, and the function is of the form y equal to a times x to the power m. Okay, so applying the least square criterion, you have s equal to the summations for I going from 1 to n of y sub I minus f of x sub I square. Okay. Remember, the form of the function is a times x to the power m, for m is any number. So you substitute f of x sub I by a times x sub I raised to the power m. I going from 1 to n of y sub I minus a times x sub I raised to the power m square. Okay. And again, to find or to minimize this criterion, you're going to take the derivative of this functions, right? Why just the derivative and not partial derivative? There is only one parameter that you need to find the formula on, which is the parameter a. So that's why we just need to use regular derivative, not partial derivative. So the condition is that the derivative ds dA is equal to 0, right? And this u the following equations. So ds dA, right? You take the derivative of this function with respect to a, you get 2 times the summations for I going from 1 to n of y sub I minus a times x sub I raised to the power m, and then you take the derivative of the inside function here to get a negative x sub I raised to the power m, and you set that equal to 0. Right. So now what you do is you divide it both sides for 2 and divide it both sides for -1. Right. So you obtain the following equations. The summation for I going from 1 to n of y sub I minus a times x sub I raised to the power m. times x sub I raised to the power m equal to 0. You distribute x sub I raised to the power m into the parentheses, you get the summation for I going from 1 to n of x sub I raised to the power m times y sub I minus a times x sub I raised to the power m times another x sub I raised to the power m. That is equal to 0. Now you break the summations or distribute the summations into the parentheses. You get the summations for I going from 1 to n of x sub I raised to the power m times y sub I minus the summations for x sub I raised to the power m square for I going from 1 to n. And again, a does not depend on I, so you can bring that out of the summation calculation. Set this equal to 0. Now you're going to manipulate these equations to obtain the value of a. So I'm going to bring the summations to the right-hand side. Get negative a times the summation for I going from 1 to n of x sub I raised to the power 2m equal to the summation negative of the summation for I going from 1 to n of x sub I raised to the power m times y sub I. And what you do is you divide both sides for the negative of the summation, and you obtain the value of a. So the value of a becomes, right, so the summations for I going from 1 to n of x sub I raised to the power m times y sub I divided by the summations for I going from 1 to n of x sub I raised to the power 2m. And this is the formula for the parameter a, given the function of this form, y equal to a times x to the power m for any m. All right, so we're gonna evaluate the value of a using the following example. So using this example, we're going to evaluate the value of c, because we want to fit the model of the form c equal to x squared to the data set using the least square criterion. So here what you do is that you have the value of n to be equal to 1, 2, 3, 4, 5. And the power m is going to be 2 in this particular case. Also, in this case, you have the table of values, and we're going to fill out the information of the table later on. But let's write down the formula for c. So c is equal to the summations of x sub I square, because m is equal to 2 in this case, times y sub I divided by the summations of x to the 4, x sub I to the 4. Okay, so here's the calculations that you need to do. So you need to do x, because you need x squared in the calculations. So you need to do x squared. And there is x squared times y. So x squared times y. And in the last column, you have x to the 4th. So this is x to the 4th. Gonna use the Excel spreadsheet in a few minutes, but let's write down the information for the x and y column here. So x is 0.5, 1, 1.5, 2, and 2.5. For the y value is 0.7, 3.4, 7.2, 12.4, and 20.1. Okay. So now I'm going to use the Excel spreadsheet to help me with the calculations. I'm going to input the value of x and y. So x is 0.5, 1, 1.5, 2, 2.5. The y value is 0.7, 3.4, 7.2, 12.4, 20.1. The next column is x squared. Right, so you set this equal to x times itself. Enter, and then just drag the formula down. The next column is x squared. So y. So what you do is this is equal to x squared times y value. Just drag the formula down. Then in the last column, you have x4. Right. And what you do is have equal, then x. So x, you can do x to the fourth, or you can just do x squared times itself. It doesn't matter. So x fourth, drag the formula down. So this is what you got, right? You're gonna write all the information into our table. So x squared is 0.25, 1, 2.25, 4, and 6.25. X squared times y going to be 0.175. It's 3.4, 16.2, 49.6, and 125.63. Just wrap it up a little bit. And x to the fourth is 0.0625, 1, 5.0625, 16 and 39.0625. So there's a lot of error calculations here. Numerical error because or the route of error that we learned in lecture 5. Okay, so we need, what do we need? What else do we need? We need this numerator here. Okay, so the numerator is the summation of x squared times y. So we need this column. So hit equal to sum, open parenthesis, choose all the column to all the value in that column, close the parenthesis, hit enter, is 195. So this is 195 for the summations. And then the summations of x4, you just drag the formula to the right, and you get 61.188. So round up to 3 decimal places. And this is what you get, right? So the numerator is 195 divided by 61.188. Now we go back to the Excel spreadsheet to help us with the calculation. So this equal to the numerator divided by the denominator, and you get about 3.87 for the value of C. So this is approximately equal to 3.187. So the function is y equal to 3.187 times x squared. Okay. And that's it for our lecture. So in this lecture, we look at this least square criterion, which is one of the most widely used criterion in mathematics and statistics. We derived the formula for the value of a and b for the case of linear equations or linear functions, and the value of a for the case of the power functions. So that's it for me. Please let me know if you have any questions.